Okay, if you thought the relativity chunk was mind-bending, this one probably is a little bit as well. Remember I mentioned that relativity largely applies at the classical and large scale of matter, and quantum applies at the tiny scale. And they're both kind of unintuitive, kind of strange to our minds that live at this scale, where we're wandering around on the surface of the Earth at our particular size, mass, velocities, and we're not traveling close to the speed of light where things get weird, or we're not close to the event horizon of a black hole where things get weird. And we're also not down at the quantum scale where things get weird, but weird they do. So hopefully this will be fun. One of the first things that got people thinking about quantum, and quantum just means size, a particular quantity, a defined quantity. One of the things that bugs me sometimes is people talk about, he made a quantum leap. It was a huge leap forward, but quantum leaps are tiny, tiny, tiny. So, but quantum just means it's a defined quantity. It's not a variable quantity. It's specific and defined. So when you heat something up, you know that if you are welding or doing other things that involve very hot metals, they glow, and initially they glow red and then they start to glow white. So they're going from that low energy infrared end of the spectrum into the visible end, and then they go into the ultraviolet end. Now, if Rayleigh-Jean's law, it predicts that quite well up to the top of the visible, but it just predicts that the energy emitted, got to go the right way on the graph, no, that way will work. The energy emitted will just keep increasing and keep increasing and keep increasing up into the ultraviolet until it ends up being approximately infinite energy emitted up in the ultraviolet end of the spectrum when you heat something. Now that's clearly not the case. When you're heating something, if it was emitting infinite energy, it would burn your face off and suck in all the energy in the universe and be bad. It was referred to as the ultraviolet catastrophe because it would be catastrophic if it were true. So clearly there's something wrong with the Rayleigh-Jean's law. Clearly it fits our empirical measurements of the world well at long wavelength, low energy light, but it doesn't fit at all at short wavelength, high energy light. So Max Planck, probably correctly pronounced Planck, but Planck is probably easier in English, suggested that the energy wasn't able to come out in a continuous flow, but that it was actually coming out in quanta, in small packets. And if you work through the implications of that notion of quantized energy emission, you end up with Planck's law, which actually does correctly map what we actually observe in nature. So what it actually does is go up for a while and then curves down in the ultraviolet rather than going up to infinity in the ultraviolet. So that was the very first, and this is in the late 1800s, the very first, excuse me, allergies, pardon me, the very first notion that quanta were important, that the size, that these discrete packets of energy were important. I mentioned when we talked about relativity that at the end of the 19th century, the 1880s and 1890s, they kind of thought that they had wrapped up all of physics and there were just a few little loose ends to still pick at, and that the photoelectric effect was one of those loose ends. And this is one of the ones that Einstein picked at and revolutionized physics in the early 20th century, 1905. So Einstein wrote a paper about the photoelectric effect in 1905. What is the photoelectric effect? If you shine light on certain metals, then electrons will be emitted from the surface of the metal. This has been known for a while, and different metals, it requires different energies of light to be shone on them. Now, this is the slightly tricky bit. If you take light of too low a frequency, if you use red light on a particular metal, you can shine it as long as you like, you can shine it as brightly as you like, and no electrons will be emitted. Now, we would expect, if light is a wave, that the waves could just keep bringing in energy And if you had a bright light, you'd have lots of energy coming in, and eventually you'd have enough energy for the electrons to get out. But that's not what happens. On the other hand, if you have blue light, which is a high enough energy, even a tiny amount will cause electrons to start coming out instantly. And the energy that the electrons have when they come out is proportional to not the intensity of the light coming in, but the wavelength, the frequency, the energy of the light coming in. So Einstein interpreted this as saying that the light was not coming in continuous waves that could come in continuously and build up energy, but coming in individual quanta, individual particles. And if the individual particle had enough energy, it could eject an electron. If the individual particle didn't have enough energy, then you could send as many particles as you want and you wouldn't get an electron ejected because there wasn't enough energy in each individual packet. So he suggested, as Planck had, that light was quantized in these little packets of energy. The energy of a particular photon is given by E equals hf, where f is the frequency and h is Planck's constant, which is 6.63, if we round it, by 10 to the negative 34. Now 10 to the negative 34 is a very tiny number. And this is the characteristic of the quantum domain, is that it happens at very tiny scales. But one photon is a very tiny amount. You might see this written as E equals h nu, which looks a little bit like a lowercase v, but curved forward. It's the Greek letter nu. And I've tried not to use that because we often use v for things and it's somewhat confusing. But in some textbooks, you'll see E equals hf. In other textbooks, you'll see E equals h nu. So I wanted to make sure that you realize that that's the same thing. Going back a bit historically, so Newton thought light was made of particles or corpuscles, and Huygens at the same time thought it was made of waves. So the original debate about whether light was a particle or a wave happened way back then in Newton's time, and both theories explain some of the behavior of light. So waves are reflected. If you see a wave hitting the side of a jetty or something and bouncing off, waves are reflected. Particles are reflected. If you see a tennis ball hitting the ground and bouncing up, it's reflected, and the angle of incidence equals the angle of reflection in both cases. Particles aren't really refracted if they go into a material of a different density, but waves certainly are refracted. So different behaviors are explained by the two models. But the double slit experiment, the fact that light interferes, so if you have two slits, light goes through the two and you get a pattern of light and dark bands on the screen behind, because sometimes the light waves come through and ripple. Let's go over here with my little dance. The light waves come through and ripple and come together and constructively interfere and create a bright band, or they come and ripple out of phase and cancel and create a dark band. Well, that's a wave thing. If you were firing particles at double slits, you would expect one bright band, two bright bands total, where the particles went through each of the slits individually. But what we actually observe is a series of fringes. So that really was, okay, light clearly is a wave. So that was considered from that time to be a solved question. Light is a wave. But coming back to the photoelectric effect and Einstein, it returns to this kind of a particle notion. In other words, there is this little discrete packet of energy. So light now has both a wave and a particle nature. We consider it to have. But I would argue that, because quite often you'll hear people say light is both a particle and a wave. I don't think it is. Light is light. Light is combined electric and magnetic fields moving through the universe, and it's neither a particle nor a wave. But we understand particles and we understand waves. We understand tennis balls and ocean waves. We can easily think in terms of those. So we use those metaphorically to describe certain behaviors of light. But light is just doing its thing, being light. It doesn't care whether we think it's a particle or a wave. And light doing its thing sometimes yields particle-like and sometimes yields wave-like behaviors. So the next place in which quantum became relevant was models of the atom. So if you had a planetary model of the atom, so you've got after Rutherford, we realized that the atom has a positively charged nucleus at the center and negatively charged electrons orbiting around it, or around it in some way. Rutherford didn't really talk about orbiting. So the notion that they orbit it's a metaphor. It's a useful metaphor, and they can gain energy and lose energy and so on. But again, what you would expect if they could orbit at any distance, as planets can, is that you would have a continuous emission spectrum. So hydrogen was the one that became particularly relevant. Hydrogen is nice because it's one proton in the middle and one electron, so it's relatively simple. All of the other elements are much more complicated. The math gets very complicated even if you just go to helium, because the two protons and the two electrons are interacting with each other, and it gets complicated. But for hydrogen, we see the emission spectrum. If we put energy through hydrogen, low pressure hydrogen, in a gas discharge tube, we'll see characteristic color bands at particular frequencies. I could go into this at considerable length about the Lyman, Balmer, Paschen and Brackett series and the sharp and diffuse lines and all of that kind of fun stuff, but that's probably still more in chemistry as well. But saying that rather than being able to orbit at any distance from the nucleus, that there were defined orbits and that it was a quantized jump of energy to get from one to the other. So what happens is a photon of energy comes in, gives the electron some energy, it jumps to a higher orbit or orbital, and then at some later time, because the electron's excited and because there's space below it at a lower energy, it will drop back down and emit another photon of light. That photon of light is what is actually causing that emission spectrum, and those emission spectrum lines are at particular frequencies, which means those photons have particular amounts of energy. So we realized that the orbitals within the atom are quantized, that there is the s orbital, which has relatively low energy, the 1s, and then the 2s, and then there are the 3 dumbbell-shaped p orbitals in the x, y, and z direction, and then there are the d orbitals, which have a ring, donut, and a number of other complicated shapes, and there are 5 of them, and again, I'm probably getting off into chemistry. But the quantum nature of the orbitals was another place in which the notion of quantized energy became highly important and relevant. The wave nature of all matter. So the fact that the electrons were behaving in these ways suggested that, in fact, they were traveling around the nucleus in a wave-like pattern, and they could only be in orbits that were whole numbers of waves, because if there was a half wave, it wouldn't kind of work as an orbit. Again, that's probably an oversimple picture, but this is at a stage when we were just learning to understand it. But Louis de Broglie talked about the wave nature of all matter. So it wasn't only light that had a wave nature and a particle nature, it was electrons as well. So this thing that we normally think of as matter also has a wave nature. And de Broglie said all matter has a wave nature, including an elephant. So even an elephant, even us, have a wave nature. And so if you use the equation P equals h on lambda, where h again is Planck's constant, which we talked about a minute ago, lambda is the wavelength of the light, and P is the momentum. So we know P from ages ago when we were talking about motion is just mv, your mass times your velocity. So if you take the mass of an elephant and the velocity of an elephant, you can figure out its wavelength. Now, it turns out that its wavelength is going to be very tiny indeed, on the order of Planck's constant, 10 to the minus 34, so not observable in any normal circumstances. So it's really only when that momentum term is very tiny. So when you've got things like the mass of an electron, which is 10 to the minus 31 kilograms, 9 by 10 to the minus 31 kilograms, then you start getting momenta at which the wavelength becomes appreciable, it becomes relevant. So the notion that all matter has a wave nature is correct, but that wave nature only becomes appreciable at very tiny scales.